Now, Mr. Sodium, please tell me why oxygen prefers you to me.
I'll do nothing to help you.
This'll make you talk. Why is each electron harder to rip off? Tell me your secret!
Ionization energy.
What is ionization energy?
It's the secret is in electronegativity.
So, the secret is in electronegativity.
This is a sodium atom. Each electron is held with a different amount of force. This outside one is a long way from the positively charged nucleus and is also repelled by the closer electrons. We can measure the work it would take to remove an electron by measuring the force times the distance it has to be pulled. This is called the ionization energy. It is measured in electron volts. It would take 5 electron volts to remove this outer electron. Moving down to the next shell, the first electron takes 50 electron volts to remove it. The next, 70 electron volts, followed by 100, 140, 170, 210, 260, and 300. The closer the electrons are to the nucleus, the more strongly they are attracted, and the harder they are to remove. In the last shell, the first electron will need 1,470 electron volts to remove it, while the last electron will take 1,650 electron volts. Of course, the only time all the electrons would be stripped from an atom is in a plasma, at very high temperatures, such as in a star. But that's physics. Chemistry happens only with electrons in the outer shell.
Good morning, coppers. There's been a mysterious murder.
Yes, Mom.
Now, some poor atom had all its electrons taken last night. Most extraordinary. I want this mystery explained. Dr. Silicon, can you give us some background?
This is a proton. It has a positive charge. It attracts an electron with an equal but negative charge. The electron orbits around the proton, forming a shell. This is a hydrogen atom. If we add another proton and 2 neutrons to keep them stable, they will attract the electron more strongly. Add another electron, and we have helium. Now, if we add another proton, the inner 2 electrons are held even more strongly. Add another electron, and we have lithium. The more protons we add, the more electrons are attracted. The inner electrons are held more and more strongly each time. Beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, sodium 11, magnesium 12, aluminum 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17, argon 18, and potassium 19. We can see that there is a very strong force holding the inner electrons in place, but the outer electrons are a long way away and attraction drops off with the square of the distance. They are also being repelled by the inner electrons. So this outer electron is very weakly held.
All right, we are doing a reenactment of the crime. The smallest, hold still. We are going to remove your outer electron. Now pull hard. Firmly held. So we pull this hard for this distance. Work equals force times distance. An ionization energy of 5.3. Potassium pretty weak force. Force times distance gives an energy of 4.3. Cesium. Pathetic. Ionization energy only 3.9. The bigger they are, the weaker they hold their electrons, and the less work it is to remove them. There must be a reason.
It is this outer electron and its ease or difficulty of removal that gives an atom its chemical properties. This is the electron that will be stolen in a chemical change. There are generally two main types of atoms. Those that lose their electrons easily, these are the metals, and those that don't lose them easily. These are the nonmetals. The nonmetals can actually steal electrons from the metals, and this is chemistry. It's a confusing example of when stealing, electrons that is obeying the law, not breaking it.
I was robbed, I tell you, robbed.
Calm down, sir. Calm down.
She took my outer electron.
Can you describe your assailant, sir?
She was round.
Anything else?
She was attractive. Here. My electron thought she was more attractive than me. I must go and get another electron or I can't face the world.
Right. I've rounded up the usual suspects. The allergen gang all have previous for stealing a single electron.
No, that's too weak. Stronger, but not the culprit. Yeah, I say. Well, she's very attractive, but she's not the one. She was stronger. There! She did it again! There's the thief!
Here, give that back, you little monster.
I couldn't help myself. I'm so attractive.
It's the electric cell for you. We'll get that electron back.
Oh, no, not the electric cell. The electron's mine. I won it in a contest, fair and square. I can't help it if I'm so attractive.
This is a chart of electronegativity. The numbers tell us how strongly each atom holds its outer or valence electrons. You can see on the left that the metals have a weak hold on their electrons. The nonmetals are on the right. There is room in the outer shell for extra electrons. The numbers show that they would hold these extra electrons more strongly than the metals. The inert gases don't appear in the chart because they have full outer shells. Argon, can I interest you in an electron?
No, thanks. Couldn't possibly. I'm full.
Chlorine, will you take one?
Thank you, just the one. That's all I've room for.
Electrons in the same shell are either beside it or on the other side of the nucleus, so there is no strong repulsion from the other electrons. Similarly, sulfur has room for 2 electrons, but attracts them less strongly. Electron sulfur?
Hope you don't think I'm greedy. 2, thank you. Delicious.
Phosphorus has room for 3 and is weaker again. Phosphorus, please do have an electron. You're a growing atom. And silicon, you could probably take 4.
Well, I can take 4, but I'm not terribly hungry.
Silicon does not attract these extra electrons as strongly as the others. The forces at this end of the table are weaker. You can see that chlorine could take electrons from any of the other atoms. When chlorine takes an electron of, say, sodium, it takes it completely. Each is left as an ion, and the bonds they form are ionic bonds. Sulfur is able to steal 2 electrons from magnesium, but this time it's not completely taken. Sulfur is a bit weaker, and magnesium is a bit stronger. And nitrogen can steal 3 electrons from aluminum. In this case, it is sharing, not stealing. The bond is mostly covalent, and only a little ionic. In the case of carbon and bromine, where they are almost evenly matched, the electrons are shared almost evenly. This is a covalent bond.
Last night, I was attacked and left with 2 extra electrons. I now have this companion. I have no idea who he is.
Right then, we'll look up the records and see who has formed for giving 2 electrons. We got beryllium, magnesium, calcium, and barium. There are others, but we'll do these simple ones first. Now, where are your electrons exactly?
Well, they are more my side than his. He doesn't seem to hold them very well.
He has an electronegativity of 1.2 and you have 3.5. Your new partner is magnesium. Yes, well, congratulations, magnesium oxide. It must have been fireworks at your wedding.
If we take the metals and arrange them in order of electronegativities, then this is the activity series of metals. We can use this in various ways. If any of these 2 metals are together, they will cause a current to flow.
All right, 20 minutes of exercise before you go to your cells.
The order is important. When we put iron in copper ions, the electrons will move to the copper ion because copper holds on to them more strongly. The voltage produced depends on the difference in electronegativity. Whenever you have atoms competing for electrons, one will win, and a voltage will be produced. In this video, we have examined this competition in the reactivity of elements. In the next video, we see how this competition for electrons is used to extract the metals from their ores.